Sieg from Carnegie Mellon University, which will talk about the concept of computation and axiomatic characterization.
Thank you very much. Of course, I would not do my ordinary obligations if I wouldn't thank the organizers for inviting me. So I do. And in addition, I gave in this room a number of times talks about computability, as some of you know. But it is a different perspective I'm trying to provide today. But before I do this, I actually wanted, well, to tell you that I was tempted during my lunch break to give a different talk. I think it's not so laughable. Quite seriously. I mean, so on Wednesday, I think, Wednesday evening, I gave a talk that was entitled Reductive Structuralism. And after the introduction, my dearest, would have been a perfect fit. But don't worry, I didn't give in to that temptation. But I wanted to draw one diagram before I go to my official talk. And the diagram relates matters in the way which I try to indicate at the very end of the session. Namely, it goes back to an image that Berners introduced a number of times, namely the image of projecting structures into something else. So the idea in this diagram is you have the structure given by an appropriate definition. And then the structure is, so to speak, projected into a more elementary domain by making use of the full formalization of the theory that is implicit in the structure definition. So this distinguished domain of mathematical objects and for Berners, it was an issue that if you had such a theory, powerful possibly, that you would project it into the finitist domain and then use the formalization to prove consistency. So obviously finitist mathematics doesn't do, but constructive extensions of the finitist domain might work. And that, as a matter of fact, has been pursued in proof theory for the last 50, 60 years, or something like that. So that you have a variety of distinguished domains, starting with natural numbers, with natural numbers plus suitably defined sets, constructive ordinals, segments of a cumulative hierarchy. And all of these domains have one particular feature in mind, at least from my perspective, namely that the objects in them can be generated inductively. And Peter Axel in the 70s introduced a very general notion of inductive definition. And these inductive definitions allow you to define natural numbers, constructive number classes, segments between the type. So that if you are worried about this reductionism, you can do it in a refined way. You don't have to think of all of set theory at once. Like segments theory, and do it relative to a domain that has these distinguished objects. And if you look at them, that is, objects that are generated by inductive definitions, there are two principles almost immediately evident for them, namely induction, and as long as the inductive definitions are deterministic, also definition principle by recursion. So in particular, if you have both of these principles, then you have a way of canonically associating domains with domains, if there are different ones in the same category. So that's all I wanted to say. So that was a temptation. I gave in to a certain extent, but not fully. Yeah, so the rest of my talk, I'm going to read more or less. First have to get used to this apparatus. Yes. So there are a number of references because the talk I'm going to give is rather survey-ish. And there is detailed mathematical work and interesting secondary literature. So I'm going to refer to these papers a little later. In any event, computations are pervasive for contemporary science and life. They are visible everywhere. However, the concept of computation emerged in an almost invisible corner of our intellectual life. It was needed to solve, particularly at the time, quite esoteric problems at the intersection of logic, mathematics, and philosophy. My analysis of the emergence of this concept provides a novel perspective on these central methodological issues surrounding computations through an approach that is rooted, you may guess, in the transformation of mathematics during the 19th century. Transformation found its most distinctive expression in the axiomatic method, closely associated with Dedekind and the early Hilbert. Hilbert was among the great mathematicians who expounded the centrality of mathematics in human thought. Late in 1930, he gave a lecture addressing the vexed question about the share which thought, on the one hand, and experience, on the other, have in our knowledge. To illuminate his view, he asserted that mathematics is, and I quote, the instrument that mediates between theory and practice, between thought and observation, and claimed that it builds the connecting bridges and makes them ever sounder. He then drew a quite dramatic consequence of this view of mathematics, and I quote again, "Our entire modern culture, insofar as it rests on the penetration and utilization of nature, has its foundation in mathematics." Today, Hilbert's claim for mathematics holds especially for those parts he helped to create for foundational studies, namely mathematical logic and proof theory. Classical analysis and its abstract extensions have been crucial for physics and result in technological developments. Logic and proof theory have become indispensable for computer science and result in computational developments. Both kinds of developments have had a revolutionary impact on our social and economic life while retaining a reflective, philosophical side. After all, we have been exploring in the first case the physical universe and our place in it, and in the second case, intelligent machinery and the human mind, that is, aspects of our cognitive capacities. Let me move from these general introductory remarks and give you a quick overview of my talk. In the first part, I describe the context for the emergence of computability as a crucial notion in mathematics and logic, with a normative philosophical component. Parts B and C analyze calculable functions on natural numbers and mechanical operations on syntactic configuration. And this analysis motivates then axioms for computable dynamical systems, the topic of Part D. And in Part D, a few connections to what I think is fascinating. Okay. Hilbert made his observations for a subject that had been dramatically transformed and expanded since its classical Greek beginnings as a systematic science. The character of this distinctly modern mathematics is indicated by its use of very special abstract structures or concepts. Such concepts do not express essential properties of privileged objects, like numbers or geometric magnitudes. Rather, they are introduced via structural definitions and applied to classes of objects with appropriate relational connections. This transformation is reflected in Dickens' essay on the nature of numbers and in Hilbert's Foundations of Geometry. It presented difficult foundational problems, which both men addressed in a variety of ways. For Hilbert, it included around 1920 the creation of mathematical logic as a tool to investigate mathematics and as a subject to be investigated by mathematical means. The creation of this mathematics has to be seen against the logical background that goes back to at least Leibniz, and I wanted to point to a few crucial steps. Leibniz, as you know, had hoped for the solution of problems when formulated in the universal language by calculation. The exhortation calculemus sticks in my mind whenever I think about calculation whatsoever. For mathematics, Dedekind shifted from calculations to proofs under the motto, in science, nothing capable of being proved ought to be believed without proof. Hilbert finally asserted that proofs are finite sequences of statements obtained by logical steps from axioms. Frege formulated appropriate logical rules and claimed that in his system, and I quote, inference is conducted like a calculation. Finally, Whitehead and Russell aimed for a full formalization of mathematics in their Principia Mathematica. Connecting considerations back to Leibniz, the issue of deciding by calculation whether a formula is provable in Principia Mathematica from finitely many axioms became one of the most important problems in mathematical logic during the 1920s. Behmann, a student of Hilbert's, gave a very vivid description of the Entscheidungsproblem in 1921. For the nature of the problem, it is a simple problem. It is of fundamental significance that as auxiliary means, only the completely mechanical reckoning according to given rules is admitted. That is, without any thinking in the proper sense of the word. If one wanted to, one could speak of mechanical or machine-like thinking. And then he adds in parentheses, perhaps it can later even be carried out by a machine. Post early investigations, after his dissertation, 1920, led him investigating exactly this problem on the other side of the Atlantic, led him to an anticipation of undecided belief and incompleteness results. Now, on this side of the Atlantic, von Neumann was convinced that the decision problem is unsolvable. Indeed, in 1927, he saw its unsolvability as, and I quote, a conditio sine qua non for the contemporary practice of mathematics to make any sense. However, he had to admit we have no clue how a proof of unsolvability would go. And the reason for this assessment was the lack of a precise notion of computation. The lack of such a concept was remedied in 1936. In a remarkable confluence of ideas, different but equivalent rigorous concepts were introduced for two informal notions. That of an effectively calculable function on natural numbers, and two, that of a mechanical procedure on syntactic configurations. With such concepts at hand, Church and Turing proved the unsolvability of the decision problem. They also addressed the methodological issue whether their concepts were adequate to represent the informal notions. The basic question, what are computations, has provoked ever since philosophical and other debates under the heading of Church's thesis, Turing's thesis, the Church-Turing thesis, or very recently, the Church-Turing thesis in quotation. The decision problem was not the only issue that called for a precise concept of computation. There were mathematical problems, like Hilbert's 10th problem of the algorithmic solvability of diagrammatical equations. there was a conceptual problem of deep interest to Gödel, to characterize formal theories and prove the incompleteness theorems for all of them, satisfying conditions of them. Indeed, that problem, that is, trying to characterize what is a formal theory in a precise way, underlies Gödel's 1934 Princeton lectures and was discussed at the time post-church. The latter actually made a particular proposal, namely to identify the informal notion of effective calculability with one defined Gödel found the idea thoroughly unsatisfactory and made a counter-proposal, namely to formulate axiomatically the generally recognized aspects of calculability and do something on that basis. However, Gödel neither hinted at suitable axioms nor at what might be done on their basis. His remarks were later interpreted as calling for an axiomatic theory in which Church's thesis or Turing's thesis could be proved as a theorem. So, one of the papers I refer to, namely the paper by Dershowitz and Gurevich, that was published in the Bulletin of Symbolic Logic in 2008, is entitled A Natural Axiomatization of Computability and Proof of Church's Thesis. Okay. I'm not going to make any remarks about it, but I just want to refer to this. The axiomatic approach I take is quite different. It's not an axiomatic theory in which I try to prove Turing's thesis or Church's thesis. It is modeled after Dedekind's approach to the question, what are natural numbers? What the numbers are as individuals does not matter, as long as their system is simply infinite. Analogously, what computations are as individual processes does not matter, as long as, and that I'm not going to tell you right now, but a little later. At this point, but I don't have to remind you, but I thought I didn't know that there was capturing here. So I did write down the definition of a simply infinite system, and I just wanted to point out that there's not a structure in the ordinary sense where you have a system of objects, distinguished element, and a function is isolated as a triplet, but it is a definition for systems of objects, and then the appropriate structural features are brought in at existentially point. These four conditions are the characteristics of an abstract structural concept and serve exclusively as starting points for proofs in arithmetic. Dedekind, as you know, established, and that should be in quotation marks, the existence of a particular system N satisfying the conditions. And he also proved the representation theorem, namely that every simply infinite system is isomorphic to this particular. Now, if you know this, then of course you obtain very directly the categoricity of the very notion of a simply infinite system. And in addition, Dedekind proved another interesting fact, namely that you have any system that is similar in his terminology, that is, there is a bijection, not an isomorphism, bijection between a simply infinite system and some other system, then this other system can be endowed in such a way that is also a simply infinite system. It's a very interesting, I suppose, in some sense startling observation. Dedekind took an enormous methodological leap when treating natural numbers via the concept of a simply infinite system and sets of objects falling under it from the same abstract perspective as the concept of a group or a field and sets of objects falling under them. Please keep this connection in mind. I will return to it after the discussion of the classical approaches that allow me to point to generally recognized aspects of effective calculability as Gödel requested. So formal calculi and absoluteness. The classical approach to the effective calculability of non-theoretic functions led mainly through Gödel and Church, but obviously also Kleene and others, to a notion of computability in formal calculi and absoluteness statements. Why did Gödel, Church, and others work with number-theoretic functions in the first place? Well, mathematicians had experience with numerical procedures, defined by iteration or primitive recursion, and ever since Dedekind knew how to solve the resulting equations. In 1931, Braun defined a class of functions broader than that of primitive recursive ones. It included in particular the non-primitive recursive axiomatic function. Braun's ways motivated Gödel's 1934 definition in the Princeton lectures, that is at the very end, of general recursive functions via two characteristics. They are given as unique solutions of recursion equations, and secondly, their values are calculable from the equation by formal rules. And he then specified particular formal rules in 1934, but there is a much more beautiful and simpler discussion of these formal rules in the slightly later manuscript from the late 30s. And there Gödel tried to analyze the way in which calculations proceed and isolated these two very elegant and simple formal rules. Pure equational reasoning. The first rule allows substitutions of numerals for variables. And the second rule allows substitutions of numerals for integrals. Gödel made, however, also the conceptual claim that 1 and 2, that is, these conditions on recursive functions, are exactly those characteristics that give a correct definition of a computable function. He thought his analysis of calculating the value of a function provided the correct definition of computable functions as recursive. Ultimately, it was a mathematical fact that made it plausible to Gödel that recursiveness captured effective calculability. Here is the fact, as he formulated it in 1936. Absolutely. It can, moreover, be shown that a function computable in one of the systems SI, systems of higher order logic, and possibly transfinite types, is computable already in S1, that is, the system of lowest type, just elementary number theory. Thus, the notion computable is in a certain sense absolute, while almost all mathematical notions, otherwise known, for example, provable, definable, and so on, quite essentially depend upon the system adopted. 10 years later, in 1946, Gödel took absoluteness as the central reason for the importance of recursiveness. Here we have, he claimed, the first epistemological notion whose definition is not dependent on the chosen formulas. Now, Gödel's 1936 framework concerned particular clearly specified higher order systems of arithmetic. And if you have such systems, this is easily proved by adapting, adopting Kleene's normal form considerations to the system, and it's quite easy. But in 1946, the absoluteness claim was formulated for arbitrary formal theories that the extended number theory. So in particular also set theory, large cardinal axioms, whatever. The latter assertion reveals, however, a difficulty that weakens Gödel's foundational claim. For its proof, what has to be explored that the extending theories are formalized. How do you do this? By requiring, for example, that the steps in arguments, in inferences, are recursive. The difficulty is also apparent in two analogous arguments, the first of which is to Church. In his classical paper from 1936, he wanted to prove that every function computable in a logic is generally recursive. He gave a correct proof, assuming the logic's inference steps to be recursive. That is the famous step-by-step argument. The crucial condition is mentioned, however, only in a footnote. Hilbert and Gentzen, in the second volume of the Grundlagen der Mathematik, discuss the notion of a function that is reckonable, in German, regelrecht auswertbar, and formulated recursiveness conditions for logical or deductive systems that guarantee in particular that the steps in such deductive systems are recursive. And then they proved that every function computable in a deductive system satisfying their conditions is generally recursive. Now each of these arguments establishes absoluteness, but they do so only if one takes for granted or explicitly requires that inference steps in the extending logical frameworks are recursive or recursive. The explication of effectively calculable functions as functions whose values can be determined in a logical calculus is undoubtedly very appealing. Hilbert and Gentzen also showed that the general recursive functions are all computable in a deductive system satisfying their conditions, so they provide in a certain sense an alternative characterization of this class of functions by allowing calculations in quite arbitrary logics. However, the question remains, why should recursiveness conditions be imposed on steps? They are supposed to be obviously elementary in some sort of way, but why recursiveness? A different approach avoids this very question by viewing computations in a more general setting. And that is content of part C, production rules and reducibility. So the classical approach to mechanical operations on syntactic configurations led, mainly through Turing and Post, to a notion of computability via production systems and to reduction theorems. This assertion may surprise you. After all, the 1936 models of Turing and Post don't look like production systems at all. And let me draw it. You have seen this undoubtedly very frequently. Tape of a Turing machine. And then there is a little machine, presumably, that has access to a particular square. And what can it do? Well, it can recognize and print symbols. It can be, in particular, internal machine configurations, like Q1, Q2, and so on. It can move to the right, to the left of the immediate adjacent thing, and commands, that is lines of a program, are written in the following form. QI, SJ, OK, QI. And what does it mean? If the machine has internal configuration QI, observes the symbol SJ, it carries out an operation, one of these, printing something, moving to the right, to the left, and possibly changes in internal configuration. Okay. Now the post worker has a different symbol space, not a tape, but a sequence of boxes. And these boxes can be marked or unmarked by a straw, for example. And there is this little post worker that can move between these boxes, carrying out exactly the operations of the Turing machine, except the alphabet consists just of 2 letters. Internal configurations are avoided by numbering the lines of the program, and it can, she can move to the right or to the left of the box currently observed. So, what does it have to do with production systems? Well, at the time, I think that, and certainly when I read for the first time Post's presentation, I'd seen he taught Turing machines earlier. I was surprised. So you had essentially the same model of computation, different sides of the different. Is it accidental? Is something better going on? But there is, and I indicate this, a deeper confluence of a conceptual character that underlies both models. Martin Davis and I wrote actually a paper together about exactly that issue. Post had presented in the 1920s the operation of Principia Mathematica, symbolic configurations, as operations on strings. And that was the explicit goal, to represent Principia Mathematica in manageable form. He proved then that the string operations can be reduced to normal production systems that have one particular string as an axiom, and then finitely many rules of an extremely simple character. G and H are particular syntactic strings. P is a variable over strings. And all the rules that are allowed are of this kind. Now, think about the intelligibility of Principia Mathematica rewritten in such a normal form. It wouldn't be very high, but that's not the point. But in some way, both thought that if Principia Mathematica can be rewritten in very simple ways, then perhaps we can solve the decision problem. Turing gave in 1936 a 2-step argument. Is argument 1, what he called the directed P intuition. In the first step, it reduced mechanical operations on 2-dimensional configurations to those of string machines. That is, machines that operate like Turing machines, but not on individual letters, but on finite sequences. And then you observe that computations of string machines are reducible to those of his letter machines with just 2 symbols. So if you look at these 2 arguments in parallel, their similarity and parallelism is rather striking. But even more so if one realizes, as Post did in 1947, that computations of letter machines, that is of Turing machines, can be very elegantly described by a production rule. So, if you think of a particular Turing machine, what is it? It is a sequence of such commands. And what Post suggested and did and used to obtain undecidability results for semi-tool systems, or semi-groups, is the following. You have so-called instantaneous descriptions. That consist of a sequence of symbols alpha. One of these machine configurations, a symbol, and possibly a sequence of additional letters. So all of the individual elements of this sequence and that sequence are elements of the alphabet. SJ obviously also. This is the only non-alphabet symbol in this instantaneous description. And what does it tell you? It gives you all the information you could possibly want to have about the state of the Turing machine. Namely, this, together with this, gives you the tape content, what is currently on the machine, on the Turing tape. This tells you in which machine configuration the Turing machine is, and its juxtaposition to the symbol says, I'm reading SJ. So whatever you need to carry out one of these commands is all given to you, as soon as you have also an appropriate production rule. And let me just indicate it right here. So assume that with a very simple command, where OK is, say, print S1. Okay. So what does it do? What does the production rule require you to do? If you're confronted with such an instantaneous description, you transform it into alpha that's left untouched. The machine configuration is changed from QI to QL. The symbol that is being observed now is printed S1, and print is sitting there. So every command of the Turing machine can be rewritten as a production rule, and then the computation of the Turing machine is just a sequence of instantaneous descriptions that starts with a particular input, and each of the elements is sequences obtained by application of production. So all the, if you wish, machine-like aspects of Turing machine are completely gone. It's pure symbol manipulation. And as I mentioned already, Post used this formulation in 1947 to prove the undecidability of the word problem for semigroups. And Turing, in 1951, extended Post's result to word problems for semigroup with cancellation by refining Post's techniques. Refining Post's techniques. Behind that, what I wanted to re-emphasize is that the operations of production systems are purely formal, no longer motivated by numerical and or logical considerations at all. And thus it was quite natural that Turing and Post were both concerned with mechanical operations on broader classes of configurations. That is, with the question, what configurations and substitution operations are to be considered? Now, Turing wrote a beautiful paper in 1950, it was published in 1954, called Solvable and Unsolvable Problems, in which he discusses undecidability results. And he discusses also, if you wish, all the methodological problems that I tried to indicate. And he does it all for what he calls puzzles and substitution puzzles. Now, what are puzzles? Anything you can think of, you can play where you have configurations, either two-dimensional, three-dimensional, you can replace, you can take out parts, you can replace them by other parts, and so on. As I said, they can be three-dimensional, two-dimensional, one-dimensional, doesn't matter. And what he claims as a sort of modified Turing system, that every puzzle can be reduced to a substitution puzzle. And what is a substitution puzzle? Post-production system of the scan. That's it. So machines don't appear in this late discussion of Turing. Only manipulations of configurations of a concrete character. Though this question was important to both, neither Post nor Turing investigated systematically. I mean, there are notes of Post in his Nachlass in which he investigates broader classes of configurations, for example, versions of cellular automata that he found interesting. But there was a pair of Russian mathematicians, Kolmogorov and Uspensky, who viewed finite labeled graphs and operations on them as providing a more adequate model of computation. My student Burns and I generalized their graphs to so-called K-graphs, Kolmogorov's graph, and introduced K-graph machines that are given by production rules. So you have graphs, you can recognize patterns in these graphs, you have production rules that allow you to replace such a pattern by something else. So just generalized production rules that not just operate on strings, but on more complex configurations. And one can show that computations of such K-graph machines are reducible to Turing machines. So we have now letter, string, and K-graph machines that are identified with generalized production systems. Operating on quite general syntactic configurations. So if one wants to address the methodological problem, where in the generation of more complex syntactic configurations does one stop? Is that a project for the rest of our life? So, as a matter of fact, that was a methodological remark you find in post-1936. He gave us a very simple model, and then he suggested, let us look at other more complex systems and reduce them to the simple. The question is there ever a point where you can say, okay, now we have included all the interesting and important syntactic configurations that might be involved. Now, for the absoluteness theorems I mentioned in the first part, we isolated recursiveness of steps as the crucial ingredient in their proofs. To obtain reductions for different classes of machines, one exploits very general constraints on their computations, namely finiteness and boundedness and locality conditions. Namely, that there is a bound on the number of symbolic configurations a machine can directly work on. And the operations of a machine must locally modify one of the configurations. Okay. So if you think of a Turing machine given by a program, finite list of such commands, or by the appropriate transcribed production rules, it's quite clear it can operate on infinitely many different configurations, and the operations modify locally. That is, if the machine is observing this particular symbol, it's not going to modify something very far away. Then the question here is, of course, as in the case of the absoluteness and recursiveness, why would I want to enforce, to impose those particular finiteness and locality conditions? And that leads me to
Yes. Quarter of an hour. Quarter of an hour until 1:30.
So that brings me to the penultimate part, structural definitions of representation. Finiteness and locality conditions really originate from Turing's 1936 paper. There Turing attempts to show that his machines can perform all mechanical operations that can be carried out by a human computer. A human being proceeding in a mechanical way. For that purpose, he strove to isolate operations that are so elementary that it is not easy to imagine them further divided. And at that point, the striking feature of Turing's approach enters, namely an appeal to the limitations of the computing agent. Constraints on cognitive capacities. What did he require? He required, in order to satisfy the normative demand that the steps should not be further subdivided, that computers, that is human computers, immediately recognize symbolic configurations used in a computation. And it is this immediate recognition, plus, if you wish, a quasi-empirical observation, that forces finiteness and locality conditions. What is the quasi-empirical observation? You have a string that should have done this on the computer, but I didn't. I mean, just imagine a long string, length 15, 19, 25, whatever, of numerals, and another one. Well, this would be too easy. And there's possibly one difference. And you're supposed to recognize that this and this string are identical at a glance. Just looking at this, looking at that. As you can do if you have 18 and 20. It's not difficult for 2, 3, 4, 5. But if you have a sequence of symbols of sufficient length, you just can't do it. So that's the, if you wish, cognitive constraint that Turing brings into the analysis and that motivates finiteness and locality conditions. So in a certain sense then, the finiteness and locality conditions are grounded in the evident sensory limitations of consciousness. And this seems to be remarkably persuasive given the intellectual context. Indeed, Gödel wrote in 1964 with evident enthusiasm, but without referring to the details of Turing's argument. In consequence of later advances, in particular the fact that due to I.M. Turing's work, a precise and unquestionably adequate definition of the general concept of formal system can now be given, the existence of undecidable arithmetical propositions And the non-demonstrability or the consistency can now be proved for every consistent fault system containing a certain amount of finitary number theory. And that's what exactly he was searching for, 1933, 1934, subsequently. So he saw Turing's work as providing the solution to this problem. And why do you think so? Well, this is a remarkable statement. Turing's work, Gödel says, gives an analysis of the concept of mechanical procedure, by this algorithm or computation procedure or finite combinatorial procedure. This concept is shown to be equivalent with that of the Turing machine. But what is Turing's analysis? What is the analyzed concept, this concept? And what is the proof that this concept, analyzed, is equivalent to that of the Turing machine? I don't know of any answers to these questions in Gödel's published work, or as far as I'm aware of in his novels. It's a wonderful formulation, but how to understand it is quite difficult. So let me return to Turing's argument that human computations that can be mimicked by letter, string, or K-graph machines. The latter are, as I discussed at the end of the last section of my talk, just finite sets of production units that operate locally on letters, strings, or K-graph. An abstractive move, analytical, I would say, allows us to articulate informal requirements for human computers, namely that they operate on finite but unbounded configurations. They can recognize a bounded number of patterns, locally operate on the recognized pattern, and assemble the next configuration from the original one and the result of this local operation. So it's just a more general description of what is happening. These requirements can be formulated rigorously as characteristics or axioms for discrete dynamical systems that consist of a state space, an operation f that is a function from S to S, and the state space consists of hereditarily finite sets, or the objects you're dealing with are finite. And such a system is called computable if this operation is computable. And what does that mean? Well, again, informally, there are finitely many patterns and local operations such that the value of this operation of the dynamical system for any argument is determined by a computation via these local operations. Now, Turing machines are computable dynamical systems, and one can prove a representation theorem. Namely, that computations of any computable dynamical system are reducible to those of Turing machines. So, let me draw another diagram, not on the blackboard, but there. So we have an abstract concept of computable dynamical systems. We have a concept of Turing machines. And we have also particular concrete computable dynamical systems and concrete particular Turing machines that fall under the general concept. But so the fact I just mentioned, namely that Turing machines are computable dynamical systems, and the representation theorem allows one then to complete this diagram. And it's not very pretty, but these green arrows. So what can I do? My limitations in PowerPoint. And there we go. So it is this completed diagram that in a certain sense reflects my answer to the question I raised after reading to you Gödel's remarks about Turing. Namely, an extension of Turing's imposed analysis of mechanical procedure has led to the abstract concept of a computable dynamical system, and that concept has been shown to be equivalent to that of Turing. So here you have made mathematical sense out of the wonderful description of Gödel's. Of Turing. No, Gödel's. So there's only one additional remark I wanted to make, namely that the guiding idea of this analysis of human computation can be used also to investigate machine computations, as Gandhi did in his 1980 papers called Church's Thesis and Principles for Mechanisms. Machines are viewed as discrete mechanical devices that can operate in parallel. Gandhi considered cellular automata as paradigmatic machines. And machines in general are taken to satisfy also finiteness and locality conditions, but not on account of sensory limitations, of course, but on account of two physical facts of a very general sort. A lower bound on the size of distinguishable atomic components of machines, and an upper bound on the propagation of signals. Then one has the motivation for finiteness and locality conditions as in the Turing case. So then one can formulate the concept of a computable dynamical piece system, parallel system, and obtain the same conceptual diagram as in the case of Turing human computing. Pretty reads to it. Okay. Okay, so with this structure, axiomatic approach, there's obviously no question of the provability of Church's thesis or Turing's thesis, or any other thesis. There's only one question, namely, do the characteristic conditions adequately capture the generally recognized aspects of calculability? I don't think they do. The representation theorem brings out the central role of Turing's machines and imposed systems for the theory of computability. Beyond giving concrete mathematical substance to Gödel's 1964 remarks on Turing and Post, these considerations provide also directions for research that has been vigorously pursued. So, the first direction concerns formal verification of mathematical theories. A formalization in principle was sufficient for the meta-mathematical investigations of Hilbert and Gentzen. Given the remarkable technological tools at our disposal, we can face the practical issue of formally verifying mathematical theorems in intelligible ways. That requires structuring proofs conceptually and uncovering heuristic strategies used in mathematics for finding proofs. The latter should involve also working with diagrams. The second is a refinement, namely going beyond formal verification of given proofs, do automated proofs. This refined formal verification program I just mentioned, articulated sensibly, leads to the quest for automated proof search. In turn, this may be the beginning of addressing Gödel's and Turing questions. What are the prospects for mathematically intelligent machinery? When focused on results that are humanly intelligent, this question presents a deep challenge to, and also, I think, a remarkable opportunity for cognitive science. We do need a better understanding of the sophisticated mathematical model. And then the question is, if you PK over into cognitive science, what are the tools used in cognitive science to obtain models of mathematical argumentation and reasoning in general? And in a certain sense, that leads back to post and again, namely to computational models for mental processes. Production systems have been used to model mental processes, in particular at my university, in the tradition of Alan Turing and Turf Simon. Other cognitive scientists have used for that purpose parallel distributed processes or artificial neural nets. The commonly used artificial neural nets used in cognitive science were shown by my student Disapia to be computable P-systems, that is, falling under this general concept of the P-system, parallel computation. Their reducibility to Turing machine computation shows then that the almost ideological controversy between symbolic and parallel distributed processes can be addressed in a methodologically refined way by focusing on the level of descriptions. One more sentence.
Stop me now. It's okay.
Having indicated three deeply related directions for research, let me articulate what I take to be the methodological core of my talk. I attempt to connect and deepen the considerations usually associated with Church-Turing thesis. However, when focusing on the mathematical aspects of those considerations, we are not led to an unusual thesis. Rather, we find ourselves in harmony with the reflective practice of ordinary mathematics, made possible by the axiomatic method. Thank you.
Questions?
So mine is not really a question, it's more a curiosity. Production, post-production system. Could you think of the instantaneous description in terms of natural deduction rules of, not acting clearly on proposition but on terms?
Yeah, sure.
Okay, and in this case, I'm curious, the proof of the disability of the word problem for semigroups. Do you have just rules with one premise, one conclusion, or rules with more than one premise?
I don't remember.
Okay, because I imagine that if you put the natural deduction, I guess that you need to have more than one premise in order to make some kind of permutation of this kind of stuff, and then look if you have a kind of subtle property, I guess. But that was a guess.
Perhaps I should answer the question. All the rules that I use are this general form.
Yeah.
So there's one premise
and one
concept.
Okay.
That's it.
Okay. Well, thank you.
Sorry, just let me make a remark. You can use the blank character dividing
Okay.
different premises as one
okay.
string.
Yeah. I mean, that's the point of having just in normal post-production systems, in normal systems, just one axiom.
Yeah, Turing apparently wrote about the computers, not the computers, right?
Yes.
And because this, according to some datations, that's was concerning the work of people trying to make computation. So his thesis then was about about the human power. On one hand about the the power of machines. Machines can do whatever we can tell them to do. So it's, if you look from this point of view, this Turing thesis seems to be much more deep than any kind of simple statement about machines. But my question is, this does not seem to be any any importance for you, does it?
Oh, it's of existential importance, right? Because it is exactly the limitations of the computing agent, us, that is motivating the finiteness and locality conditions that are crucial for Turing's argument to show that anything a human computer can do can be mimicked by one of his machines. That is absolutely central.
Yeah, but I mean, but this also puts some limitations on what machines and we, in connection to machines, can do. It puts limitation on our relationship to machines.
That I don't see as clearly as you do. But I mean, the attempt of characterizing or doing for machine computation what Turing had done for human computation, that was the motivating aspect for Gentzen, who happened to be also a student of Turing's.
Okay. So actually it's a question that's motivated by a conversation that I had with Alfred some time ago. So it's good that you're here. So there are these results, I guess, well, it's fairly recent, on the non-standard models of arithmetic, and then what's different between the non-standard models and the standard models is that there are nice recursive properties of the standard models that the non-standard models don't have. And this has motivated some people to say, see, this is why they're standard, right, and not the non-standard. That's why these are right and those are wrong. Having this conversation with Bob, they said to me, yes, but look, maybe the way to look at it is that the non-standard models are going to teach us a new way to think about computability, right? So it's not so much, maybe the standard ones tag more closely our old conception of computability, but there's nothing that prevents this very concept of computability to undergo changes, in theory, right? And then perhaps there will be this, of course there was talk of quantum computability, now that's not as fashionable as it used to be, but I mean, so basically the question is, of course you're taking the informal notion of computability as it was already at this stage of development in the 1930s, and this is what Turing and Church and Post, etc. took at their starting point. Great, fine, and did wonderful things with it. But nothing prevents the very informal concept of computability from undergoing changes. And if that's the case, then perhaps a different concept of computability might not then be captured by these formal developments that spring out of this work. I just wonder how much you think that computability really is that and cannot be something else, or whether this is like a concept that could, in theory, at least undergo some sort of development.
Look, I mean, that we might have a broader concept of computability or narrower ones that is more concerned with efficiency, yes. Of feasibility, yes, of course. But I mean, that's why I emphasized Turing wanted to capture human computability, and that was exactly what was required. I mean, look, I mean, the decision problem was solved, right? I mean, there were no machines, quantum computers, or whatever around that was supposed to solve the decision problem. We were supposed to solve it. Yes.
Sure, but I mean, my point is, it was a completely successful program back then with the concept of computability then that he was taking separate. But what if some very fundamental changes occur in the concept of computability that we find attractive for other reasons, and then you might need a different formal treatment.
Yes, of course. I mean, look, already the distinction between human computation and machine computation. I mean, I have done this. So if you look at the machine computation part, this is very complex. And, you know, just indicate the complexity. So you have a certain complex state. You can recognize in it lots of different patterns. And then you operate on these patterns locally to get something out. And then you have to put it all together in a coherent way. It's absolutely non-trivial. But in the end, there's nothing new, and that is the exciting part. If you have these general physical conditions, they inform locality and finiteness conditions in exactly the same way as sensory limitations for human computing. And it's wonderful to speculate. I'm happy at the moment that I could do what I could do. So.